Welcome back to ECE 441A 541A. We were having a spirited discussion prior to coming on air, and hopefully you are having a spirited discussion while you're watching this. Few announcements. A lot of things are due on Wednesday of next week, the 7th of December, lab number 3. You'll want to make sure and get in and do that. Apparently there's a contest on how quickly you can finish that. Project, if you're in 541, that's due on Wednesday. Homeworks 9 and 10 are due on Wednesday, and there is some additional material that should help you get through the phase lag and the phase lead controller design on D2L that wasn't presented in class, but it's some MATLAB material and some material on steady state air, how to derive the velocity gain constant. Homework 9 is dealing with the Bode plot design. Homework 10 is the state space design, which we will talk about today. And the numbers on the TCEs are not that high, so we need to improve on that. So there's been a lot of discussion about extra credit this morning. I don't know what it is in the air. Maybe it's the cool temperature, but people are wanting to get warmed up with extra credit. So I'm taking some things under advisement. Stay tuned, and we will see about extra credit. And one thing I thought about before or after I made these up last night is maybe there might be office hours other than Wednesday, since you do have the two homeworks due on Wednesday. Maybe I'll see if my schedule allows for a Monday or a Tuesday office hour. That would be the extra office hour. Speaking of Tuesdays, a week from next Tuesday is the final exam. And that won't be for extra credit. It's mandatory, and it starts at 10:30. It's a little later than when we normally start, and it's not a Monday, Wednesday, Friday. So be sure and come to the correct room. It's in this room unless you're taking it elsewhere, and you know if you're taking it elsewhere. You'll know how to take that. Today what I want to do is cover all of Chapter 11. No, but we'll cover some of it, a fair amount, and it's dealing with full state feedback design, and I want to work through an example, and that example hopefully will lead us into, we'll get far enough to show how these feedback gains do impact the block diagram, and that might give you a more intuitive feel for what's happening with full state feedback design. If we have time, we'll get to how we introduce a reference input. There will be a different gain on the reference input and how we can incorporate that to minimize our steady state error in this design approach. Let's start by answering or examining a question, which is what is possible with full state feedback? And here, apparently, a lot of you really enjoy matrices. So I want to, hey, matrices have a bad rap. They're pretty nice. They're pretty handy. You want to be comfortable with them. And now in Chapter 11, that's how we are describing our system. We're modeling it with the state space representation. We have this vector x, and it could be as simple as a vector that's 1 by 1, meaning it could be scalar. It could just be an x variable. But in general, x is tall and thin. It's just one column wide, and x contains all of our state variables: position, velocity, temperature, pressure, current, voltage, you name it. But that's now related to our system matrix A times the state vector. And then we have our input coming in through the input matrix B, and our input is U. X of t in general then is n coordinates tall and one column wide. And we will be talking about system behavior or system dynamics, and this A matrix, we haven't introduced any feedback. This is now our open loop system matrix. And if we wanted to know how our system was going to behave in the open loop, and somebody said, what are the open loop dynamics? What could you do if you now had access to the A matrix? How could you tell them something about the behavior of your system in the open loop? What would you be looking for or examining? I know if you're listening to this online, you've heard all of that discussion and response coming back at me. I apologize that it all came at once, so you maybe didn't hear it. But the open loop dynamics are influenced by the A matrix, the eigenvalues of A. The eigenvalues of A are the poles of your open loop transfer function, and they govern the dynamic behavior of your system. Or here, let me just say the eigenvalues of the system matrix will give you your open loop dynamics, and I might just refer to that as lambda of A. What will happen typically is you're not very happy with the behavior of your open loop system. It may vibrate or behave in a way that you don't like. Maybe the overshoot is too big, maybe it's too slow. You want to change the dynamic behavior. Today we're going to do that like you did in lab number 2 with feedback, and we'll do it with full state feedback. Here our feedback is now going to be U of t. That's the input that we're going to inject into the system, but we will now create that input out of a linear combination of the state vector, and the linear combination is coming in through the gain matrix K. K now is overloaded. K now is a vector or a matrix. It's not just a scalar parameter. Plus n R of t. This is now our full state vector, and R of t is our reference input. And if you wanted to think about this in terms of what it might look like, U, depending on if you had 1 input, 2 inputs, 3 inputs, U, if it's 1 input, will just look like that in terms of size. It'll be 1 by 1. It'll be a scalar variable. But now K has to be compatible with your state vector, which if your state vector is n rows tall, K has to be n columns wide. But the height of K will be the same height as U. And we also have then our n matrix, which could be a scalar if R of t is also a scalar. As an example, suppose that x is n by 1. U, let's say that we have m inputs. M typically in this class has been 1, but m could be 2, 3, 5. It could be bigger in general. And our reference input vector, although we've typically kept that as some scalar variable, it could be bigger dimensionally. It could be p different reference inputs. If this is the case, then you already know how big K is. How big is K? Or what are the dimensions on K if I've now given you, so this could be a final exam problem, and that would be a gift, I would hope, on the final. What is the dimension of the K matrix if you now have the dimension of X, the dimension of U, and the dimension of R? What do you know? If this guy is now M by 1, and this is N by 1, and this is P by 1, everything has to be compatible. Meaning, whatever you end up with from the product of K times X, that has to be how tall in terms of rows. M, it has to be the same number of rows as the input. And how many columns wide is K? It has to be compatible with X, so this is now N columns wide. So this is now an M by N matrix in general. Most of the time we have one input, little m is 1, and we maybe have 2 or 3 states, little n is 2 or 3. How big is capital N? How tall does it have to be? How many rows have to be in the matrix N? It has to be compatible with U, so it's now M rows tall. And how wide is N? P. It has to be compatible with R, and so it's M by P. There's your gift if that was a final exam question or problem. You should be able to just sketch those rectangles that contain K, X, N, and R and relate those to U, and you now have your answers for the dimensions of K and N. Let's now use this feedback structure, U is equal to minus Kx plus NR, and apply that to our open loop system. Meaning, let's just replace U with this new expression in terms of K, X, N, and R. And we might refer to this as closing the loop. Where now we have x of t is a x of t plus b, and now we're replacing u of t with this minus k x of t plus n r of t. There's our u of t. There's our input. So we're letting u of t be minus k x of t plus n r of t, and this might be referred to as full state feedback because we're feeding back, we're assuming we have access to every one of these state variable components: position, velocity, temperature, pressure, voltage, current, whatever is making up the state vector. That's now getting used or scaled by the elements that we have to design in the K matrix to give us what we want. And what do we want? Now we have the structure of our system, x dot equal to a mess on the right, but we can put things together. We can collect common terms, meaning we can now say that we have x dot is equal to a minus bk times x of t. Those all have x common to them on the right. And we have plus b in r of t. And what we will notationally typically say is now our closed loop system matrix is F, and that's this A minus BK. And if somebody says, well, how did you select the dynamics? Now you have to find the eigenvalues of F. So what we're trying to do is we're trying to pick parameters in the K matrix to change the eigenvalues of F to something more desirable, something that we would prefer versus what they were in the open loop, which were at A. Or we have changed the system dynamics from the open loop, which we could just say is A, to F, which is A minus BK. Let's look at an example of how this might play out. We now are assuming a second order system. We have two state variables, x sub 1 and x sub 2. Our A matrix is now all 0 first column and a 1 minus 1 in the second column. And our input matrix, we're assuming we only have one input, and it's entering our system in the second row. Here is our A matrix. There's our B matrix, and if we wanted to, we could maybe keep track of the output Y, and let's just say that the output is just the first coordinate of our state vector. So this is now our C matrix, and now we've come full circle. We now have come back to our ABCs near the end of the semester. I think we started talking about ABCs earlier when we were talking about modeling systems. Now we're back to modeling the system. We've just done it now, not in a transfer function, but we could find that transfer function using one of our cheers from this state space representation. What are the dynamics or the open loop eigenvalues for this system? And if you've had a linear algebra class or some matrices, the eigenvalues are jumping out at you and they're screaming. They're cheering, actually. They're saying, here I am, here I am. This is an upper triangular matrix. And in that case, if you have a triangular matrix, upper triangular or lower triangular, your eigenvalues are on the diagonal. So what variables are on the, or what values are on the diagonal of this system matrix? We have one eigenvalue is 0, or we have a pole at the origin. That's what that eigenvalue of 0 says, that these are the poles of our open loop system. And we have a second eigenvalue at -1. And you're familiar with that system, a pole at the origin and a pole at -1. And you now can visualize that in this complex S-plane with your x's. Since I mentioned the cheer, I might as well bring it back. What is the open loop system? What is G of S in terms of the ABCs? So now we're relating this state space representation to what you've been playing with the last month or two. This is now C, SI minus A inverse times B. And just for grins, let's do that. Let's compute that. That's now C, which was 1, 0, SI minus A, so that now we had S's on the diagonal, and we subtract from those S's the A matrix, which should give us S minus 1 in the top row and 0 and S plus 1 in the second row. We need to invert that matrix, and that will be a symbolic inverse because S is a complex frequency variable. times our input matrix B. But a 2 by 2 matrix, you don't even need to go out and spend a lot of money for a calculator to do that for a 2 by 2. You just have to remember a trick, how to find the determinant, and then you just interchange the diagonal elements and change the signs of your off-diagonal elements, and that's the inverse of that matrix. Or we still have our C matrix. What's the determinant of that matrix? We want to put that in the denominator. It's 1 over S times S plus 1, that's the product of the diagonals, minus the product of the off-diagonals. That's now our determinant in our system, or the denominator in our system. And what did I say to get the rest? We interchange the diagonal terms and we negate the signs of our off-diagonal, and now so this has now been translated into that. That's the inverse of that matrix. And we don't want to forget our input matrix that's sitting over here that now needs to manipulate that. So really, if it's confusing, just factor out that denominator and keep it aside, and now do the matrix multiplication to get your numerator piece of that expression. Or we now can say that G of S, let's do what I said. Let's factor out that denominator piece, and now we have our output matrix times S plus 1, 1, 0, S, 0, 1. And we have a lot of ones and zeros floating around. Let's go ahead and multiply the right two matrices first. And that 0, 1 column is really just going to pull off the second column in that matrix of S's and 1's. Meaning we now have 1 over S times S plus 1. There's our denominator. There's our output matrix, but now 0, 1 is really just going to pull off the last column in this second matrix, or the middle matrix. And now what's the product of 1, 0 times 1, S? That's just 1. So our numerator collapses to giving us a system, G of S, that's now 1 over S, S plus 1. Where are the poles of that system? 0 and minus 1. And those should be the same as the eigenvalues of A. And they are. Now, we are not going to derive this result, but if you wanted to know, can I arbitrarily locate my open loop poles anywhere with full state feedback, then you can check a matrix that's called the controllability matrix, and if it's full rank, you can control your eigenvalues, or you can put your closed loop eigenvalues anywhere you want. So let me just say that let's go ahead and check controllability. And that simply is a way of looking at how the system matrix A and the input matrix interact or play together. And do they play nice together? If they do, then this controllability matrix will be full rank, and you'll be able to place your closed loop poles wherever you want. That's theoretically. You don't want to put them at minus infinity, because what does that do in the lab? If you try to really push the system, what happens to the mechanical system? It probably doesn't, it's not happy, is it? It may start vibrating, it may start shaking violently. It's not happy with trying to push it beyond its limits. So there are practical limits to this theoretical result of arbitrary location of your closed loop poles. But here, we're really asking or answering the question, what can be done using full state feedback. That's what we're answering by doing this controllability check. Let me simply give you the expression for this controllability matrix. I'm going to call it a script C, and now what we do is we just start building up this matrix with different stacks of columns. And then the first set of columns, we just put in the input matrix B. Then we multiply the system matrix times B, and that's our next set of columns. And we just keep doing that. We multiply AB times A on the left to obtain A squared B. And if this is on a Friday night, you may want to do this if n is 100. Now you have A to the 99th, 99 A's, never mind. So, our little n is not very big, typically, is it? Little n is maybe 2. So how many times do you have to multiply A and B together? If little n is 2, you have A raised to the 2 minus 1, A to the 1. You just do B, AB, and you're done with this controllability matrix. In our example, that's exactly what's happening to our controllability matrix. It's as involved as B, and what was B? That was 0, 1. And what happens when we take A, wherever A was, and multiply it by B? The product of A with B, what does that give me? Gives me a 2 by 1 result. It better, because it better be compatible with the B matrix. And the B is saying, oh, just pull off the last column in A. So AB is really going to be 1 minus 1. And that's now the extent of creating this controllability matrix. What we want to do is look at the rank of that. Then the rank just means, does it have full row rank, whatever that means. But if it's square, you can just compute the determinant. And if you get a non-zero determinant, you know that C has linearly independent rows. So full rank says, do I have linearly independent rows in this? Or do I have little n linearly independent columns? I'm going to just say that's row of the C, where this is now the rank. And in fact, I do. These rows are linearly independent, are they not? Maybe we don't know what we're... The columns are different. The rows are different, correct? 0, 1 is not the same as 1 minus 1, so they are linearly independent. The rank is 2, or if you... So the system is controllable if C is square, then you can check the determinant of C. And the determinant of C better not be too hard to compute. That's 0 times minus 1, the diagonals, minus the off diagonals. And what's that result? That's minus 1, and that's not equal to 0, and that's what you're wanting. It doesn't matter that it's negative. It can be negative, it can be positive, but this now says that we have linearly independent rows, we have linearly independent columns, our system, our controllability matrix is full rank. We can now place our closed loop poles arbitrarily in the complex S-plane. That's what we were really trying to answer. Now that we know that, let's go ahead and do that. Let's use full state feedback. to try to place the closed loop poles or the closed loop eigenvalues of this F matrix, which is A minus BK, at, let's just pick some points. Let's say -5 and -10. Which of those is the dominant eigenvalue? I now am saying I want my closed loop poles to be at -5 and -10. Where were my open loop poles? 0 and -1. So these are faster, correct? They're further into the left half plane. Which of these two dominate? -5 or -10? And how do we determine which one dominates? If you looked at this, this is going to give you a mode, this -5 of e to the -5t. One at -10 will be e to the -10t. Which one lasts longer, the response? Which mode stays active longer? E to the -5t or e to the -10t? E to the -5. It's the pole that's closest to the origin. That's the one that's dominating. So if somebody said, what's the settling time of this system, you would focus on that slowest eigenvalue and say, oh, I need to look at e to the -5t and determine when it gets to 2% of the original value. That's your 2% settling time. If this is now where we want our closed loop poles, we're really saying that we have a desired denominator expression or a desired characteristic polynomial. We now are saying our delta sub d desired is now made up of the product of these two factors. So now if I can keep my class in order, what do I have? If I'm now multiplying this out, what do I obtain? S squared plus 15s plus 50. That's where we want. And where was our open loop? It was at s times s plus 1, was it not? So now we're trying to change that to this. In order to do that, we need to see what the system matrix of the closed loop system looks like in terms of k, and k is variable. K contains a k sub 1 and a k sub 2. This is now 0, 1, 0, -1. There was the a, minus b, and now we know the dimension of k. K has to be compatible with b and a, so that now we have k is a 1 by 2 matrix. We just had one input and we had two state variables. I'm going to do this in a few steps, but this is now what's going to happen when I multiply b times k in the top row of that product. I have all zeros, don't I? I have 0 times k1 and 0 times k2. I now have zeros. And the 1 times that just puts k in the bottom row of that product bk. And my F matrix now, if I combine these, produce in the first column 0 and minus k1, and in the second column and there is my closed loop system matrix, and I want to be able to manipulate k1 and k2 so that the eigenvalues of F give me -5 and -10. That's all I'm wanting to do. And I can find the eigenvalues of F by looking at the determinant of the lambda I minus F matrix, or finding the characteristic polynomial of that matrix. So let's now find the characteristic polynomial of F, or that's now this determinant of SI minus f. And if I use straight vertical lines to indicate the determinant, I have S times the identity matrix. And that identity matrix needs to be compatible with F, and F is 2 by 2, so the identity matrix is 2 by 2, minus the F matrix, which I just computed. And if I put all of those pieces together into one matrix, I have S in the 1, 1 entry. I have K1 in the 2, 1 entry. And in the 1, 2 entry, what do I have? I just have minus 1. I have 0 from the first matrix, and I have minus 1 from the second. And now in the bottom, the 2 by 2, or the 2, 2 entry, I have S minus that 2, 2 entry in the F matrix, and so I now have S plus 1 plus K sub 2. And I want to now find the determinant of that matrix in terms of K1 and K2. Or Si minus F is now the product of the diagonals. This is again a 2 by 2, so the determinant is pretty easy, minus the product of the off diagonals. Pardon? Thank you. I was just making sure everybody was paying attention. This now should be the product of the off diagonals. Minus 1 times K sub 1. Must be Friday. The last Friday of the semester. All right, don't start cheering. That wasn't a cheer. That wasn't a request to cheer, but apparently it produced a cheer. Now, if this is correct, let's multiply that out, and I now have S squared plus 1 plus K sub 2S plus K sub 1. And what am I wanting to do? I'm wanting to pick K sub 1 and K sub 2 to produce eigenvalues of minus 5 and minus 10, but I already know what that desired polynomial looks like. That's S squared plus 15S plus whatever it was, 50. So now this I want to set equal to my desired characteristic polynomial, which was S squared plus 15S plus 50. This is what we want. We want to select our feedback gain values, K1 and K2, to make the black polynomial equal the blue. That's what we're trying to accomplish. And all that requires then, in this case it's pretty trivial, but let's just say in general you would want to equate the coefficients, and that might lead you to two equations and two unknowns, which this does, but one of those equations drops right out. We immediately know what K sub 1 is. But if we look at the S1 coefficient, that says we want 1 plus K sub 2 to equal 15, and S sub 0, so this is actually a decoupled set of equations. This now says K sub 2 is 14, and the S sub 0 says K1 is equal to 50. And now we have our full state feedback structure. Now we can say our input U of t is now minus K x of t plus n r of t, but we found K. K1 was 50, K sub 2 was 14. We're multiplying that by our full state vector plus n times r of t. Or U of t is now minus 50 x1 of t minus 14 x sub 2 of t plus n r of t. So if we have access to the full state vector, we can measure or we can sense x sub 1 and x sub 2, I now simply take x1, measure it, scale it by 50, negate it, and use that to form part of my input u. I measure x sub 2, scale it by 14, negate that, combine that, and now I have u of t. If I didn't want to force this system in any particular direction by the choice of r, if I just wanted to have a system that responded to initial conditions or kicks, and then how does it shake, you would have r of t equals 0, and its shaking would be governed by eigenvalues of -5 and -10, based on these weights of k1 and k2 on the full state vector. So let's now see what we have in terms of a block diagram. We now have r of t coming in through n. We have, let me do a couple of different summing junctions. What was our original system? We had x1 of t, and we had x2 of t. And how were those combined? What was x1 prime? Was it just x sub 2 in the A matrix? Wow. x1 dot is x sub 2, and x sub 2 dot is minus x sub 2. And u comes in through x sub 2. So this now says that we had 1 here. Let me put the minus sign. Here's u of t, and there's y of t, and this was our open loop system. Whoops. What's highlighted in yellow is our open loop system. And that might be a final exam question. Find the state space representation, and I might just give you this all integrator block diagram. What would you do? You would label the outputs of your integrators as the state variables and then write your state variable equations. What we're wanting to do now is use full state feedback. And in this case, we said, oh, measure x sub 2 of t and scale it by 14, let's say minus 14, and let that be part of u. Measure x sub 1, scale it by minus 50, and let that be part of u. And now what do we have? Now we've changed the dynamic behavior of our system so that the blue, the black, and the red now all combine to give us a dynamic behavior that has closed loop poles at -5 and -10. Is it clear what we're doing here? We started out with what's highlighted in yellow. Now we have introduced full state feedback, and we now have this. What we want to do now is figure out how do we select in this scenario. What would be one goal that you might be after? If you now say R of t is my commanded direction, maybe this is an airplane, and Y is the heading of that airplane, and now you want to know with what is R, I want to maybe go to 10 degrees, so R might be 10 degrees. You would like Y to do what? Go right to 10. You would like to have very small error. If Y went to 1 and you commanded it to go to 10, you might not be very happy. Meaning, we want to now select capital N, this gain on our reference input to allow us to have zero error between when we put in an R and when we measure Y. So that now if I say go to 10, it will go to 10, and how will it dynamically go to 10? What will its dynamics be influenced by? What's the settling time? It's influenced by that one pole at -5, isn't it? The dominant pole. And the other pole is at -10. So -5 and -10, because we've picked -14 and -50 as our gains to adjust or to weight x1 and x sub 2, we know that this highlighted portion of our system in blue is going to respond with dynamic behavior influenced by e to the -5t and e to the -10t. That's how it will respond, and what we want to do now is make the choice of capital N such that we have zero error between R of t and Y of t. Questions on that? So how do we do it? Now what we can do is we can look at our closed loop system. We now have A minus BK x of t plus Bn R of t and Y of t is equal to C x of t. This is now our closed loop system. Can we find the transfer function between the reference input R and the output Y? And this is just a modified version of our cheer. This is now, if we wanted to simplify things, we have F. And this is now, if we wanted to simplify things, maybe a B bar. And so now instead of my ABCs, I have my FB bar C. You didn't learn your FB bar of C in elementary school or preschool, but you're going to learn it now. So how do you use FB bar C in our cheer? What's the closed loop transfer function? And typically I may call this actually T of S. This is now the transfer function between Y of S and R of S. That's C times SI minus F inverse B bar, which is B in. Is that clear where that came from? We're just trying to find the closed loop transfer function between R and Y. And our system matrix now is F, and if we expand this, F, now this T of S, in terms of the original matrices, it's SI minus A minus BK inverse B times N. And this is our closed loop transfer function. At this point in the game, what do we not have specified? What have we not yet specified in this collection of variables? K. K we've picked. K was 15 or 14 and 50, right? We're given B, we're given A, B, and C. That was our open loop system. We haven't picked N, have we? So we want to find N to give us zero error. If I'll just give you the punchline, most of this is now 1 over S squared plus 15S plus 50 times N. And if I want a DC gain of 1, if I want zero error, Do you see how I would fix N? If I want a DC gain of 1, I want TC of 0 to be 1. I now am saying, oh, I want 1 over 50 times N to be 1. So that now I know what N needs to be to give me 0 error. N needs to be 50, and now I have all of my parameters specified in my full state feedback configuration. And we'll pick up at that point on Monday.